Okay, the final subtopic of the organic chemistry topic is polymers. And in particular, we're going to go back and look at some addition reactions some more, which we introduced a little bit before, and look at the importance of those for many of the products that we use in our everyday lives. Let's get into it. Okay, so if you weren't already aware, polymers is another word for plastic. So all these things we're talking about are plastics, and there's a huge amount of plastics in our lives that we use every day, and they're all polymers. So the first thing we need to be able to do is identify the repeating unit of a polymer given the structural formula of a section of the chain. So I've got 3 chains here, and if we look at those in this top one, we basically, the repeating unit would be this here. So you might get asked to circle the repeating unit, and you can see that unit just repeats itself over and over and over again within that chain. So that polymer there is PVC, polyvinyl chloride. That's what's used to make a lot of the plastic water pipes. If you think of most plastic water pipes, they're made of PVC. There's also a lot of other materials that are made of PVC. Duct tape is made of PVC. So yeah, very common polymer. That's an example of an addition polymer. I'm going to talk more about addition polymers in the next slide, but the way we can tell that that is an example of an addition polymer is it just has this continuous carbon backbone. So the backbone of the polymers is all carbons. Down here, we have an example of a polyester. We've got this ester group here that joins it together, and that ester group is basically repeated through the structure. Like there's another one here. So Dacron is used for making materials. Sails are often made of Dacron, but like medical implants and some of that is also made of Dacron. And down here we have a polyamide. This happens to be nylon 66. So a lot of clothing is made with nylon, but a lot of ropes and stuff like that are also made with nylon, and lots of other things are made with nylon as well. So we're going to focus on the addition type polymers like PVC next, but you need to be able to identify that repeating unit within the structure of any polymer. Next year we took more at polyesters and polyamides in both the organic and the materials part of the Stage 2 chemistry course. So let's keep moving and look at some of these important addition polymers and how they are produced. So firstly, better introduce the word monomer. Monomer is a small molecule that joins together to make a polymer. Draw the structural formula of the addition polymer that could be produced from monomers that contain one carbon-carbon double bond given the structural formula or the monomer of the monomer or vice versa. So you basically need to be able to either, given the monomer, work out what the polymer is, or given the polymer, go backwards and work out what the monomer is. So there's a lot of these addition polymers and they're used all the time in our lives. And I'm just going to talk about 2 in detail, and I'll mention a couple of others, but I could have listed even more. So firstly, we'll go back to PVC, and that starts off with the monomer. Vinyl chloride is its common name. If we used a systematic name, it would be chloroethene. Ethene because it's got a carbon double bond and a chlorine. You don't need to know about chloros this year, but you probably can see how that makes sense based on the stuff that we've looked at. And what happens in these addition polymers is, well, let's just think about what a chemical bond represents is a shared pair of electrons. So this is telling us that there are 2 shared pairs of electrons, so 4 electrons in total between these 2 carbon atoms. And when an addition polymer forms, one of these shared pairs moves, and instead of being between those 2 carbons, it joins in between, it uses that to join onto the next carbon. And then this one moves and joins onto the next carbon, and that just keeps happening on a continual basis, and you get left with this structure here. So there's no carbon-carbon double bonds anymore because all these shared pairs of the second shared pair of electron has moved to between an adjacent carbon, and it just gives you that continuous structure. So if you identify that repeating unit, and then basically you need to work out, well, these are fairly straightforward. There must have been a carbon-carbon double bond there, so you can go back the other way. Another one, this monomer here, tetrafluoroethene, tetra meaning 4, fluoro meaning fluorine, 2 carbons meaning eth, ethene meaning carbon-carbon double bond. And again, a similar thing happens here, that one of those pairs of electrons moves and is used to join to the adjacent carbon, and we get this continuous structure here with all the fluorines, and this is Teflon. So Teflon is used to coat a lot of frying pans and all that. It's got a very high melting point, but it's also very scratch resistant, a very durable polymer. So another one you might come across. Now, I won't go through, sorry, just see something missing there. PET, that should say. I won't go through these in whole detail, but just a couple of other monomers that are used a lot. This here is ethene, 2 carbons, also commonly known as ethylene, and that's used to make polyethylene, or abbreviated PET. PET is used to make a lot of plastic drink bottles. It's also used to make a lot of ropes and that sort of thing. And another one here, I've done a skeletal structure here, but you've still got this carbon-carbon double bond at the top that can keep joining, and this is styrene, and this is used to make polystyrene, which is probably what you know as common foam and all that sort of thing. So you don't need to remember all those, I just think it's interesting to have those examples, but you do need to be able to basically, given the monomer, work out how they join together to make the polymer, or give the polymer, go backwards and unwind them if you like, and work out which monomer they came from. Hopefully those couple of examples will help, and it's probably one of those skills it's just best to practice and work it out. Okay, let's keep moving. So finally, you need to have a bit of an understanding of the properties of polymers and what causes those polymers. So the properties of organic polymers depend on interactions between the chains. So if we think of our chains here of PVC, or our chains of Teflon, or our chains of polystyrene, or even the Dacron or the polyamide in nylon, any of those sort of things, generally what determines the properties of those polymers is the sort of cross-links you get between those long polymer molecules. If the cross-links are weak, i.e. they are formed through dispersion forces or dipole-dipole bonding, or even hydrogen bonding, which are all secondary bonds or secondary interactions, those polymers all tend to be relatively soft, have a low melting point, they're easy to recycle, they're what we call thermoplastic. So thermoplastic means it softens when heated, it's moldable, and then it will harden when it's cooled down, which makes it easy to recycle, remold into a new shape. If you have strong cross-links here that are formed out of covalent or ionic bonds, which are primary bonds, those bonds within molecules are generally much stronger than the bonds between molecules, which are the secondary bonds or secondary interactions. These polymers tend to be more rigid, they have higher melting points, they're difficult to recycle, and they're generally referred to as thermoset plastics. So thermoset doesn't soften on heating, they'll often catch fire before they'll melt when you try and heat them. So in terms of recycling, generally the thermoplastics are preferable, but they may not always be as hard and durable as some of the thermoset plastics. But there is a lot more detail we could go into about those bonds, but we don't need to do that really. Just recognise, are they secondary bonds or primary bonds forming the cross-links between all the chains, and then that will determine whether it's a thermoplastic or a thermoset and what properties it has. So that's it for the organic chemistry topic. Cheers.